Okay, random variables. How do we describe and summarize these random events? We're going to look at another way to start organizing some of our probability type of problems. So a random variable is a variable whose value is based on some random event. That's probability, randomness. Two types of random variables, and we've seen these previously in the class. You have a discrete random variable where you can list each of the individual outcomes. Flipping a coin, right? Heads, tails, heads, tails, heads, 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 tails, tails, tails. Making a basketball shot, we can count the number of shots, right? There's a discrete number. You can't make 6.5 shots. It's 6 shots, 7 shots, 8 shots. And the other, if you go back and look through some of your previous information, was a continuous random variable. Now this is where the outcomes can take on a really an infinite number of values. One of the easiest ones to think about is height. You know, it's not that you have to be either 6'1" or 6'2". You can be 6'1 and a half, 6'1 and a quarter. You know, there's a wide range of values that the height could take. Arrival times at an airport, it's not that the flights just show up at 1 o'clock or 2 o'clock. They can show up any time, right? Down to the second. And if you wanted to get specific enough, you could go parts of a second. So really, there's an infinite number of values that these arrivals can take. So really, when you're looking at anything normally distributed, so now in this unit, we're going to start to bring in that normality. We're going to bring that back. So let's take a look at an example, grade distribution. So let's say that this intro stat class had the following grade distribution. 21% had A's, 43% B's, 30% had C's, 5% had D's, and 1% of the students in this college class didn't pass. So the first thing as we do these random variables is we want to define a random variable. So for us, great variable to use is x. So we're going to call x the grade of any randomly selected student. So let's say that we're going to do some kind of study and we're just going to start randomly selecting students out of the class. We're going to start looking at the probability that we get certain students. So what we'll do is we'll turn their letter grades into numeric values. So just like in any academic setting, at least as far as I know, we'll call an A a 4, a B a 3, C is 2, a D is worth 1, and an F is 0. So really as we start to set up these random variables, we're going to set up tables that look a lot like what you see down here at the bottom of the screen. These tables are going to become very, very helpful for us in the sense that our data is going to be organized and we're going to be able to start pulling probabilities very easily from this table. So the trick over the next few days is to make sure that we're setting these tables up correctly. So the probability that we select a 4-point student would be 0.21. A B student or a 3.0 student would be 0.43. And we got 30%, 5%, and 1%. Now that we've got our data in an organized way, we can start to use that distribution. And all of a sudden, what's the probability a student receives an F? So in other words, the probability that x equals 0. So go to your distribution table. Here's 0. The probability that we get that, 0.01. So not very likely that somebody fails. Right? What's the probability of receiving a D or an F, or an F or a D? So really, x equals 0 or x takes on the value 1. So we know from previous information this means to add, and like we did last unit, we always want to subtract an overlap, but here it's impossible for a student to make a D and an F at the same time, so there is no overlap. So the probability of a D was 0.05 or an F 0.01, 0.06. One more look at it. What's the probability of a student receiving a grade higher than a C? So the one nice thing about the table is we could go up here, we can take a quick look, and as a quick reminder, this is just going to help me out very quickly. An A, a B, a C, a D, or an F. Just by having it organized this way, a grade higher than a C, well, that can include two different grades, right? It could be an A or a B. So the probability that x is greater than 2, 0.21 plus 0.43. So 64% of the students had something higher than a C. Another way that you could have written that, higher than a C, we could have also written that probability that x is greater than or equal to a B. Right? And it'd be the same exact thing, 0.21 plus 0.43. It's just a matter of, do we want to include it? Do we want to use the inclusive greater than or equal to, or do we just want to use greater than 2? So greater than or equal to 3 is the exact same thing as greater than 2. All right? So let's say that we're going to flip a coin. Let's look at another example. Very basic way, very quick explanation of that, but go a little bit more in depth with it. So we'll take a look at a little bit more advanced of a problem, flipping a coin here. So the random variable, we'll call it the number of times we get a head after tossing a coin 4 times. So let's start to set this thing up, some kind of probability distribution. So we could either get 0 heads, 1 head, 2 heads, 3 heads, or 4 heads, right? Again, these values right here, these are what y can take. Sorry about this. I don't know why that's flipping back and forth. It really wants to show up. So what we'll do is we'll go ahead and start the table. So y could take on the value of 0 heads, 1 heads, 2 heads, 3 heads, or 4 heads. So what we want to start to think about is filling in this probability distribution just below. So how can these things happen? So there's a total number of ways, right? 2 times 2 times 2, heads or tails, and heads or tails, or heads and tails, heads and tails. There's 16 total events. I'm going to flip a coin 4 times, and we'll go more in depth here in just a second. So basically, among 0 heads, 1, 2, 3, or 4 heads, there's 16 different outcomes. And so we're going to go ahead and split those up. So ways that we could get 0 heads. Really, there's only one way that we get 0 heads. It's tails, 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 and tails. 1 heads, you could have a head, then 4 tails. You could do tails, heads, tails, 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 heads, tails. Or I could do 3 tails, 1 heads. All right, 2 heads. All right, let's make sure I can get all these. Heads, heads, tails, tails. Heads, tails, heads, tails. Heads, tails, tails, heads. Tails, heads, heads, tails. Tails, heads, tails, heads. And then I think finally, tails, tails, heads, heads. 3 heads, we could have heads, 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 tails. Heads, heads, tails, heads. Heads, tails, and then 2 heads. We could start with the tails and then get 3 heads in a row. And then finally, there's only one way to get 4 heads, and that's to get 4 heads. And if I've done that right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 total combinations. So let's look at the probability of each event. The probability that we get a tails, and a tails, and a tails, and a tails. Right, so that would be 0.5 times 0.5 times 0.5 times 0.5 for a grand total of 0.0625. Right? So that's the probability that we get 0 heads. Right? That would have been the probability that y equals 0. All right, let's just look at one of the, another one of the random events here. 2 tails and 2 heads. So again, the probability of a tails is 0.5 and a heads, well, that's 0.5. Then we go 0.5 again, 0.5 again, right? The probability of heads or tails, if it's a fair coin, it's going to be 50-50 the whole time, 0.0625. Right? There's a lot of different options here. So the probability that we get tails, heads is 0.0625. The probability that we would get a tails and then 3 heads in a row, the probability of that particular combination, we could find the probability that we get this particular combination, right? 2 heads and 2 tails. One thing to notice, Both of these two situations would include the probability of, two heads. So there's multiple ways to get some of these things. So if we, excuse me, let me go back in here. I lost my recorder. So those two red stars, excuse me, are both the probability of two heads. And again, if you do every potential outcome has the same probability. But what makes this a little bit uh, uh, more in depth, more complex, is there's different number of outcomes within each one. So the probability of each one of these outcomes, right? The probability of this occurs is the same as the probability of this occurs. However, you've got four of those options right there with one heads. There's six of these 0.025s, right? There's 6.0625, right? You flip a coin four times, probably you typically would expect two heads or two tails. That's the most likely outcome. There's just a lot of different ways to get that. So the way that we're doing that in the table, there's only one way to get zero heads, so it's one of those 0.065s. Well, there's four ways to get the one heads, so we do 4 times 0.0625. And the same way here, there are 6 ways to get uh, two heads, so we're going to multiply 6 times 0.025. There are 4 ways to get 3 heads. And then finally, there is only one way to get 4 heads. And so what we can do with that then, go ahead and drop all those values in here. And here's the best way to check, right? At the end of the day, anytime we're dealing with probability, the probability of the sample space must equal 1. And if you were to add these up, if these sum to 1, that doesn't guarantee that you've done it right, but there's a good chance that once you sum all your probabilities, if they equal 1, you've probably done something the right way. So, answer a few questions. What's the probability we get at least 2 heads? So take a quick look. At least 2 heads. That would be 2, 3, or 4. And this makes it a little bit easier too, as opposed to trying to do any kind of complement rule. We can go straight to the table, right? At least 2 heads would be 2 heads, or 3 heads, or 4 heads. Right? The probability of at least 1 head, right? So really, you look at the table, at least 1 head, that'd be all of these put together, right? So you could add 0.25 plus 0.375 plus 0.25 plus 0.0625. We also know the probability of at least 1 head, so y is greater than or equal to 1. That's also equal to 1 minus the probability of no heads. So either way, because the sample space equals 1, we could also do 1 minus all those things, or 1 minus, excuse me, 1 minus 0.0625. So our complement rule still works here. So you could use that, or again, the probability that y is greater than or equal to 1. We could also just use the fact that, look at the chart and add all those up. 0.375 plus 0.25, 0.0625. Either way, right, both of those are equal to 0.9375. It's very likely that in 4 flips of a coin, we're going to get at least 1 head. So one other quick example. Suppose these randomly selected customers are going to buy monkey shaping kits. Sure, why not? And they can either get an electric or a gas model, right? Who doesn't want a good monkey shaver? But, some people might prefer an electric model versus gas. So assuming that they make each choice independently, Consumer reports that 40% of people prefer electric models, 60% tend to choose a gas model. This is a little bit different simply because we're not a 50-50 shot anymore. The setup is very, very similar to what we just did. We just use different numbers. So, again, the probability that we get an electric is 0.4. The probability of a gas is 0.6. So find the probability at least 2 of 4 customers. So the probability that 2 or more customers will choose the electric model. Right, so let's take a quick look. Define the random variable. So we'll let x be the number of people out of 4 that choose the electric model. So go ahead and do the sample space. So out of the 4 people, 0 could want an electric model, 1, 2, 3, or all 4. Right? But each probability is going to be slightly different. So find the outcomes for each event, and we'll, like we just did, E for electric, G for gas. And then we'll find the probabilities associated with each outcome, and then the total probability of the whole event. So the probability that 0 people, and we said that X was the number of people that chose electric, so that would be gas, 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 and gas. 1, so we could have gas, 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 electric, gas, gas, electric, gas, gas, electric, gas, gas, or electric, gas, gas, gas. 2, gas, gas, electric, electric, gas, electric, gas, electric, gas, electric, electric, gas, electric, gas, gas, electric, electric, gas, electric, gas, and then finally electric, electric, gas, gas. 3 people prefer electric, so the first 3 customers could prefer electric, the first 2, and then the last, the first person through the door, oh, excuse me, and then, so all I'm doing right now is just writing out all the potential outcomes. And then finally, for 4 people, excuse me, that would just be all 4, oh, prefer electric. Right. So the probability of 0 people, gas times gas times gas times gas. Again, give me just a second. What did we say? The probability of gas was 0.6. Right? So that'd be 0.6 times 0.6 times 0.6 times 0.6. Probability of 1. Right? So in other words, you'd have to put all of these together. Well, all 4 of these have 3 G's and 1 E. So really what you're looking at 4 times gas, gas, you want 3 G's and 1 E. And that should be equal to, I don't know why it slid all the way over there, 0.3456. Let me go back real quick and get you a number here. That one was equal to 0.1296, excuse me. All right, the probability we get 2. So 2, how many possible combinations are there for 2? Well, if you count up there, there's 6 possible combinations, and that includes 2 gases and then 2 electrics. So it's very similar to the previous problem, as I wrote right on top of it. That's 0.3456. Probability we get 3. Again, that was going to be 4 times. Now we've got 0.4, 0.4, 0.4. So now we've got 3 E's. And then 1 G. And then finally, there's only one way. Right? There's exactly one way to get 4 E's. And that's just going to be 0.4 times 0.4 times 0.4 times 0.4. That equals 0.0256, excuse me. Once we've got our probabilities, drop them into the chart. At least 2 out of the 4. So again, the probability that x is greater than or equal to 2. At least 2 out of the 4. Add those things up. So at least 2 is a little bit different than what we saw last time. The table makes this a lot easier. Again, it's one of those things, once we have the table, the math is not going to be the difficult part. So, random variables.